Welcome to the Deep Dive. We're on a mission to cut through the noise, take the information you've shared, and pull out the truly valuable nuggets of knowledge, giving you a fast track to being well-informed.
And today, we're plunging into a really fundamental area, beginning software engineering.
That's right, you've sent us excerpts from this book, and it's pretty comprehensive. It looks at everything from the initial idea for a piece of software.
All the way through to its long-term maintenance, yeah.
Exactly. We're talking about chapters covering things like RD, rapid application development deployment strategies, different models for the software development lifecycle.
Agile methodologies, too, which are huge now for adapting to change.
Right, and maintenance, metrics, why measuring things matters, and the really core stages, design, development, testing.
And even figuring out what people actually need in the first place. Requirements gathering.
Plus project management to kind of, keep it all together. And there are appendices, glossary, index, the whole works.
So our aim with this deep dive, really, is to build a strong foundational understanding of these core software engineering ideas.
Okay.
We want to show how all these different stages aren't just like separate boxes. They're really interconnected, part of a bigger picture.
So it's about seeing the whole process.
Yeah, and grasping why a structured approach is so important if you want to build software that actually works, is easy to use, and crucially, can be maintained and evolved over time.
And, even if you've never written a line of code, stick with us. Because these principles we're talking about.
Like understanding user needs, managing projects, teamwork.
Exactly. Those apply way beyond just building software. So let's dive right in. Why does software engineering even matter? It sounds simple enough. Have an idea, write a program.
Well, yeah, it might seem simple for, a small personal project. But the book really highlights that for anything with real scope, things can go wrong. In countless ways, it can get complicated really fast.
Okay, like what? Give us some examples of these pitfalls.
Well, the classic one is building the wrong application entirely because you misunderstood what the users actually needed.
The difference between what they say they want and what solves the real problem.
Precisely. Or you end up with software that's just riddled with bugs, super frustrating to use, a nightmare to fix later.
Well, maybe it works technically, but the interface is just confusing. People can't figure it out.
Exactly. Bad usability. And the book even mentions situations where a perfectly good application fails anyway due to external factors, market changes, maybe internal politics, things outside the code itself.
Wow. Okay. It sounds like a bit of a minefield then.
It can be, and that's where software engineering comes in. It's like a toolkit, a set of techniques to help you navigate that minefield.
To avoid those traps.
Yeah. It's about making sure the end result is effective, usable, maintainable, and hopefully meets the schedule and budget too.
And it helps you stay flexible, right? For when unexpected things pop up.
Absolutely. It helps control what the book calls that random whirlwind of chaos that software development can sometimes feel like.
I like that. Bringing order to the chaos. Okay, so we see why it's important. How do you even start building the right thing? Where does that begin?
That brings us to a really crucial point. Understanding the customer. Who are you actually building this for?
Right.
The book stresses identifying them could be external clients, internal teams, maybe even yourself. And then, interacting with them, really talking to them.
To figure out what they need.
Yeah.
But you mentioned that distinction earlier, wants versus needs. That seems key.
It's fundamental. Customers might ask for specific features, but you need to dig deeper to understand the underlying problem they're trying to solve. That's the real need.
Okay, so you talk to them, you figure out the needs. Then what?
Then you translate that understanding into requirements documents. Think of these as a contract, almost, a shared understanding.
For the customer, it clarifies what they're getting.
Exactly. And for the development team, it clarifies what they need to build. It becomes the blueprint, guiding everything.
And it helps manage scope, right? Like the book's example with the video tutorial request.
Perfect example. If that wasn't in the original requirements, you use the document to evaluate it. Is it essential now? Does it fit the budget, the timeline? Maybe it's for version 2.
It helps keep things focused. Avoid feature creep.
Precisely. It manages expectations. And this whole process, figuring out needs, it's often iterative, not a one-off thing.
So you don't just lock yourself away for weeks writing requirements.
Well, yeah, the book kind of jokes about that being inefficient. You make your best guess, show the customer something concrete, maybe a quick sketch or a prototype.
And then get their feedback.
Exactly. Refine your understanding based on what they say. It's much more dynamic, collaborative.
That sounds way more effective. Less chance of going completely off track.
For sure, especially on bigger projects. Having several people involved in gathering requirements, talking to users, that works better, even if it takes more coordination.
Okay, so requirements. The book breaks them down into different types, which I found helpful. Functional and non-functional.
Yeah, that's the main split. Functional requirements are about what the application should do. The actions, the features.
Like generate a report or
Yeah.
allow user login.
Yeah.
The verbs.
Exactly. Non-functional requirements are about the qualities of the application, how well it does those things.
Okay.
The book uses that FURPS plus acronym: usability, reliability, performance, supportability.
And the BUTS plus AC is for.
Kind of a catch-all. Design constraints, like it has to run on specific hardware.
Sure.
Implementation requirements, maybe a certain language. Interface requirements, how it talks to other systems. Physical requirements even. The whole context.
Got it. So it's not just features, it's the illealities and constraints too. And good requirements have certain characteristics. They can't just be vague wishes.
Absolutely not. They need to be clear, unambiguous. Everyone needs to understand them the same way.
Consistent too, right? Can't contradict each other.
Definitely. And prioritize, you need to know what's most important. And crucially, verifiable. You have to be able to test if a requirement has actually been met.
The book had good examples, like reduce appointment start windows is vague.
Right, but reduce start windows to a maximum of 2 hours for 90% of appointments. That's specific, measurable, verifiable.
Makes a huge difference for developers. But sometimes requirements conflict, don't they? The book mentions fast, good, cheap, pick two.
Ah, yeah, the classic trade-off triangle. You often can't have everything. You need to make choices, prioritize, maybe sacrifice a bit of performance for better reliability within the budget.
So speaking of prioritizing, when you have a huge list, how do you decide what to do first? The book mentions Moscow.
Yeah, Moscow is a neat way to categorize requirements. Must have, should have, could have, and won't have, at least for this version.
Okay.
It gives stakeholders a clear framework to decide what's absolutely essential versus what's nice to have. Helps focus the effort.
Makes sense. So how do you actually get these requirements initially? Where do they come from?
Several ways. The most obvious is just talking to customers and users. Direct interviews. Observing users in their actual environment is really powerful too. You see things they might not even think to tell you.
Like watching how they struggle with the current system.
Exactly. Studying existing systems, especially if you're replacing one, is key. And then there's brainstorming.
Brainstorming.
Yeah.
Getting ideas flowing. The book mentions specific techniques, though, not just a free-for-all.
Right. Osborne's method. Quantity over quality, initially, no criticism, encourage wild ideas, then combine and refine later.
Okay.
There's the sticky note technique, nominal group technique. Everyone writes ideas anonymously, group discusses, then votes, avoids groupthink.
And idea passing, where an idea goes around the group for additions.
Yeah, another way to build on initial thoughts collaboratively.
And the book has tips for good brainstorming sessions. Comfortable room, snacks.
Always helps. But also recapping the user problem first, setting time limits, allowing a bit of topic drift sometimes for creativity. It's about creating the right environment.
It sounds like getting requirements right, even if it's not the coding part, is absolutely critical.
Foundational. Get this wrong. And no matter how well you code, you might build something useless.
Okay, requirements nailed down. What's next in this whole journey? The SDLC.
Exactly. The software development lifecycle. SDLC for short. It's basically all the tasks involved, start to finish.
So requirements, design, coding.
Implementation, yeah. Then testing, deployment, getting it out there, and maintenance. The whole shebang.
It sounds very linear when you list it like that. Step one, step two.
Well, that's the catch. The book emphasizes these stages are deeply interconnected. It's not always strictly sequential.
Okay. So decisions in one phase affect others.
Absolutely. Requirements influence design, design impacts implementation and testing. You need to think about them together, not in isolation. It's more like a cycle or even a spiral sometimes.
A holistic view.
Mm-hmm.
And there are different models for this SDLC, different ways to structure it.
Yeah, different frameworks. The book mentions predictive versus adaptive models and iterative versus incremental.
We'll get more into the adaptive iterative side with Agile later, I guess.
Exactly. For now, just know there are different philosophies, different game plans for how you arrange these basic steps.
Okay, game plan set. We know what to build from requirements. Now, how do we build it? That's design, right? The blueprint.
Perfect analogy. Design is the blueprint. And the book splits it into high level and low level.
High level first. What's that about?
It's the big picture view. The major components of the system, how they'll interact, key environmental assumptions, hardware, other software it needs. but not the nitty-gritty code details yet.
Like the overall architecture. The book had an interesting point about considering the team structure here.
Yeah, very practical. If certain pieces of the system are tightly coupled, maybe share a lot of data,
Yeah.
it makes sense for the teams working on those pieces to be closely coordinated, maybe even physically co-located if possible. Helps avoid integration problems.
Makes sense. Like designing a house, the plumber and electrician need to coordinate. So
Yep.
what specific things are part of high-level design? User interface.
Yep. How will users interact? Menus, buttons, single screen like a tablet app. Just sketching the basic navigation flow and feel.
Hardware specs too.
Done.
Easy to forget the physical stuff.
Totally. Printers, servers, network gear, any special instruments it connects to, what does it need to run, how does it all connect?
And the software architecture itself. Monolithic versus client server.
Right. Monolithic is one big chunk. Simpler maybe to start, but harder to change parts later. Client server splits the work. Rule-based for systems driven by logic. Component-based uses reusable building blocks.
Trade-offs there, right? Monolithic, simpler to debug maybe, but distributed systems have network issues, complexity.
Exactly. Pros and cons for each, depending on the project's needs. Scalability, maintainability, team structure all play a role. Then there's data design.
Databases, relational tables, fields, keys, or maybe something simpler built in.
Yeah. And sketching the relationships between tables is key early on. The book also makes a great point about data evolution.
How it might change over time.
And whether you need audit trails, who changed what, when, that adds work. Plus, sometimes there are legal rules about deleting old data. It's data lifecycle management.
And outputs aren't just reports, right?
No. Could be printouts, web pages, data files, images, audio, video, even sending emails or texts, all the ways the system communicates out.
Security, huge one. User permissions, error handling.
Crucial. Needs to be baked in from the start, not bolted on later. Who gets access to what? How do you handle unexpected situations gracefully?
And don't forget training and documentation.
Often overlooked, but vital for users to actually use the thing effectively.
Okay, the UML diagrams. Sounds a bit technical.
It can seem that way, but UML Unified Modeling Language is just a standard way to draw pictures of the design, a visual language.
To communicate the structure and behavior.
Exactly. Class diagrams show the components. Use case diagrams show user interactions. Sequence diagrams show how messages flow over time. State machine diagrams show how things change state.
The book gives basic examples. Classes with properties and methods, states and transitions, actors and tasks, message timing, helpful visual tools.
Yeah, it helps everyone get on the same page. So that's high level. Low level design gets more specific.
Right. Diving into the implementation details, object-oriented stuff, classes, objects, inheritance.
Exactly, like the car inheriting from vehicle example. But the book warns against misusing inheritance too, the supplier inheriting from person example. Sometimes composition has a relationship is better than inheritance is A.
And data normalization comes up again here. 1NF, 2NF, 3NF.
Yeah, structuring the database properly to avoid redundancy and those weird anomalies when you try to insert, update, or delete data keeps the data clean and consistent, like organizing your files properly.
Okay, blueprint detail, time to actually build it, development phase, turning design into code.
This is the part everyone thinks of as programming, but the book rightly says the edges are blurry. It overlaps with design and definitely with testing.
And testing should happen early and often.
Constantly. Ideally, testing code as you write it, or even before you write it, test-driven development, which we'll see in Agile. Catching bugs early save massive headaches later.
What tools do developers use here? IDEs?
Integrated development environments, yeah. They bundle everything. Editor, compiler, debugger, often source code control too. Essential workbench.
Source code control sounds vital, especially for teams.
Absolutely critical. More so than for documents, the book argues. It tracks every single change, who made it, when, why, lets you revert if needed. See exactly when something broke. It's line-oriented, tracking individual text line changes.
It's like a time machine for your code. Essential. The book mentions algorithms briefly, predictable versus heuristics.
Yeah, predictable ones always give the same answer. Heuristics are more like rules of thumb for complex problems, where a perfect solution is too hard or slow to find. They aim for a good enough answer quickly.
And top-down design for tackling complex code, breaking it down.
Same principle as an overall design, but applied to coding a specific complex function. Break it into smaller, manageable steps. Divide and conquer.
The book has some great programming tips, too. Writing for humans, not just computers.
So important. Code is read far more often than it's written. Clarity matters. which leads to comments.
Right, explaining the why, not just the what. The book warns against the just barely good enough approach here.
Yeah, skimping on comments and docs creates technical debt. It bites you later when someone, maybe you, has to understand that code.
And avoiding side effects and methods, what's that about?
A method should ideally just do what its name suggests. A side effect is when it does something extra, unstated, like modifying a global variable unexpectedly, makes code harder to reason about and test. If you must have one, make it obvious in the name.
Conditional compilation for debugging code. Sounds useful.
Lets you include extra logging or checks during development, then easily remove that code for the final release. Cleaner, faster production code.
And using exceptions for errors.
Forces you to handle potential problems properly instead of the program just crashing or ignoring errors silently. Makes code more robust.
Finally, technical debt. What is that again?
It's the long-term cost of taking shortcuts now, like delaying necessary refactoring, cleaning up messy code. You save time up front, but pay later with increased complexity, bugs, and slower development. It's like a loan you have to repay with interest.
Okay, code written. How do we know if it's any good? Testing time.
Absolutely crucial, not an afterthought. Testing happens at multiple levels.
Developers test their own stuff.
Yep. Then dedicated testers look at it with fresh eyes. Then integration testing, making sure all the pieces work together.
And different types of testing, too. Functional, compatibility.
Destructive testing, try to break it. Performance testing, stress testing, push its limits. Usability testing, is it easy to use? Security testing, find vulnerabilities. Lots of angles.
The book mentions black box, white box, gray box testing.
Black box. You test based only on requirements, don't know the internals. Inputs, outputs, does it match specs?
White box.
You know the internals. You look at the code, design tests to hit specific code paths, check the logic.
And gray box is a mix.
Kind of. Some internal knowledge, but mostly testing from the outside, like a user would.
The book has good testing habits, too. Test when alert. Seems obvious, but...
Yeah, debugging tired is a recipe for making things worse. Also, test your own code, but get others to test it too. Fix your own bugs to learn. Think before changing code. Test your tests.
And a process for fixing bugs. Reproduce, isolate, fix correctly, test the fix.
Look for related bugs, make sure the fix didn't break anything else. It's a disciplined approach.
The book mentions estimating bug counts and bug tracking systems.
Yeah, estimating is tricky, maybe related to complexity. Bug tracking systems are essential, though. Log every bug, its status, new, open, fixed, tested, closed, priority, who's working on it. Vital for managing the process.
Code coverage comes up, too. What's that measure?
It tells you what percentage of your code lines were actually executed by your tests. High coverage doesn't guarantee no bugs, but low coverage definitely means parts haven't been tested. Helps find blind spots.
Okay, tested thoroughly. Time to get it to users. Deployment.
Yep. And you need a deployment plan. Step-by-step instructions, what could go wrong, workarounds, and, critically,
A way to roll back. Undo the deployment if it goes badly.
absolutely essential. You need an escape hatch.
The point of no return concept sounds a bit scary.
It's the point where going back is harder than pushing forward, even with problems. You want to delay that point as much as possible during deployment.
Different deployment strategies. Direct cutover, phased, parallel.
Direct cutover. Flip the switch. New system is live. Simplest but riskiest.
Phased rollout.
Gradually introduce it to certain users or certain features, lower risk, get feedback.
Parallel operation.
Run both old and new systems side by side for a while. Safest but most complex and resource intensive.
The book mentions variations to staged deployment, gradual cutover, all aimed at minimizing disruption. And always expect mistakes, have that rollback plan ready.
You bet. Murphy's Law applies heavily to deployments.
Okay, deployed successfully. Phew, we're done.
Right.
Not quite. Now comes maintenance, the long haul. And this can be a huge chunk of the total cost.
Often the majority of the cost over the software's lifetime. Years, sometimes decades.
Why so costly?
Well, software often lives longer than expected. User needs change constantly. And new environments emerge, new operating systems, hardware. Plus, new bugs get discovered.
The book categorizes maintenance tasks. Corrective, adaptive.
Corrective is fixing bugs. Adaptive is modifying it for new environments. Perfective is improving performance or adding small new features not in the original scope. And preventive is making changes now to avoid future problems like refactoring.
Ah, refactoring again, cleaning up the code.
Yep. And the book warns about the second system effect during maintenance or replacement projects.
Trying to make the replacement too perfect and overly complex.
Exactly. Adding every bell and whistle because now you know better can lead to disaster.
Bug tracking is still key in maintenance.
Absolutely. You need to track issues reported by users. And refactoring is important when code gets messy, duplicated, hard to understand, but maybe not for every tiny bug fix.
And maintenance itself can introduce new bugs.
Oh yeah, it's an ongoing cycle. Fix one thing, test carefully, make sure you didn't break something else.
Okay, it's a marathon, not a sprint. How do you manage the whole project, keep it on track? Project management and metrics.
Crucial area. Management sets goals, tracks progress, keeps the team focused, and executive support is vital.
For resources, decisions, navigating hurdles, defining the business case.
Exactly. The project manager handles the day-to-day. Refining requirements, tracking tasks, dealing with problems, managing risk, communicating status.
Tools for scheduling. Task tables, PERT charts, Gantt charts.
Yeah, PERT helps find the critical path, the sequence of tasks that determines the shortest project duration. Gantt charts visualize the schedule, dependencies, timelines, accounting for non-work days.
But the book warns. Garbage in, garbage out. These tools are only as good as the time estimates.
Precisely. And estimating software tasks is notoriously hard.
Why harder than, say, building a bridge?
More unknowns, creative problem-solving, changing requirements, reusability isn't always predictable. It's less tangible.
How to get better estimates then?
Experience helps. Break tasks down small. Allow buffer time for the unexpected, but beware Parkinson's law. Work expanding to fill time.
And Brooks's law. Adding people to a late project makes it later.
Classic. The communication overhead swamps any potential increase in work output.
Risk management is key too. Identifying potential problems.
What could go wrong? How likely is it? What's the impact? What's our plan B? Proactive problem prevention.
Tracking progress and doing project postmortems afterwards.
Learning from success and failure. What worked, what didn't. You need data for that, which brings us to metrics.
Measuring things, like when defects were created. Earlier is worse.
Much worse, yeah. More costly to fix, more impact. Ishikawa diagrams, fishbone diagrams help find the root cause of problems.
So metrics help understand the process, predict things, improve.
That's the goal. Measure attributes, derive metrics, create indicators, spot trends, improve the process. But teams sometimes resist metrics tracking. Time-consuming, subjective.
Common complaints. It needs to be done thoughtfully. Normalizing metrics helps, like bugs per 1,000 lines of code, KLOC, to compare different sized projects.
Or function point analysis. Counting inputs, outputs, files, adjusting for complexity.
Another way to estimate size and complexity independent of the programming language used.
Okay, that covers the more traditional plan-driven view. Let's switch gears to agile methodologies.
Right. Agile came about largely as a reaction to the limitations of those predictive models, especially when requirements change frequently, which they often do in software.
The Agile Manifesto. Core values.
Individuals and interactions over processes and tools. Working software over comprehensive documentation. Customer collaboration over contract negotiation. Responding to change over following a plan.
Sounds much more flexible, people-focused. It is, and the 12 principles expand on that. Things like satisfying the customer via early and continuous delivery, welcoming change, frequent software delivery, daily collaboration, motivated teams, face-to-face conversations ideally, working software as the measure of progress.
Sustainable pace, technical excellence, simplicity, self-organizing teams, reflecting and adjusting. It's a whole philosophy.
Absolutely. And it leads to common practices.
Like big visible boards, information radiators.
Yep. Frequent meetings like the daily stand-up, short iterations or sprints, customer reviews after each iteration, constant feedback loops.
The book covers specific agile methodologies, extreme programming, XP.
XP has its own values: communication, simplicity, feedback, courage, respect, and specific practices like pair programming, test-driven development, TDD, continuous integration, small releases, coding standards, collective ownership.
Scrum is another big one. Roles like product owner, Scrum master, dev team.
Right. Artifacts like the product backlog, sprint backlog, events like sprint planning, daily scrum, sprint review, sprint retrospective, very defined framework.
Rapid application development fits here too.
It's often seen as an early agile-like approach. Emphasizes short cycles, iteration, user involvement, prototyping, code reuse, case tools. has specific phases: requirements planning, user design, construction, cutover.
Advantages like speed, user buy-in. Disadvantages like needing committed users, potential scope creep.
Exactly. Trade-offs, as always.
And others mentioned briefly: Crystal, FDD, Kanban, AUP, DAD.
Yeah, a whole family. Crystal adapts to project size criticality. FDD focuses on building feature by feature. Kanban is all about visualizing workflow and limiting work in progress using a pull system. AUP is an agile take on the unified process. DID is a hybrid, goal-driven, scalable framework.
Wow, quite a landscape of approaches within Agile itself.
It really is. Different tools for different situations, but sharing those core agile values and principles.
Well, this has been incredibly insightful. A real deep dive into beginning software engineering. Let's try and recap the biggest takeaways.
Sure. I think the main thing is that software engineering provides vital tools to manage complexity. To build software that actually works is usable, reliable, maintainable.
And understanding the customer, getting those requirements right, that's absolutely foundational.
Definitely. Then having a structured life cycle, whether predictive or adaptive, like agile, matters. Design needs thought. Testing has to be rigorous and continuous. Deployment needs planning. Maintenance is ongoing.
And Agile offers that flexible way to deal with the inevitable changes.
Right. For me, the real aha moments are seeing how interconnected everything is. You can't silo these stages.
Yeah, me too. And the human element that kept coming up. Communication, teamwork, continuous learning. It's not just about code.
Absolutely. And for you listening, even if you're not a coder, these ideas, clear requirements, managing complexity, collaboration, adapting to change, they apply everywhere. Planning a marketing campaign, organizing an event.
Managing any complex project, really. Understanding team dynamics, managing expectations, appreciating the complexity behind the tech we use daily.
Exactly. The principles are broadly applicable.
So a final thought to leave you with. In this tech-driven world, understanding, even at a basic level, how software gets built, the process, the challenges, the principles, empowers you. You become a smarter consumer, a better collaborator, maybe even a more effective innovator in your own work.
So maybe ask yourself, what other complex processes in your life or work could benefit from a more structured yet adaptable approach like the ones we've talked about today?
Thanks for joining us for this deep dive.